Okay, I come back and I already start recording the second half of our class. So let me share my screen again and we can continue. Okay, at the initial state, before the slider move down the slope, we have the kinetic energy 1/2 mv square at that position. And for the gravitational potential energy, I set the datum point here at the center of mass height. So at this point, the gravitational potential energy is 0. How about the position 2? The position 2, we need to find the speed at the position 2. The position 2 means at this position. Here is the 0 position, and here is the position 2. At the position 2, the kinetic energy is 1/2 mv2 square, but we still don't know the v2. So it's 1/2 50 and v2 square, and we just leave it in the terms of the unknown v2. How about the potential energy? The potential energy at point 2. The distance on the slope, will be 3 feet plus x equal to 4 inch. The distance on the slope is 3 feet and 4 inch. How about the position in the vertical? Direction? What should be this distance? For this distance is the distance from the edge of the slider to the point that the spring deforms. You need to note that the distance that the center of mass of the slider move, it also moves with the same distance here. And the height of the CG change to the position 2 also equal to the vertical distance here. So MGH2 mass is 50. G, the unit G is equal to 9.81 meter per sec square in the SI unit, right? But what we know is we know that 1 foot is equal to 0.3048 meter. So we can find G in the unit of the foot per sec square. And by use the calculator, G in foot per sec square will be 32.17. And the vertical distance or the height too, the H2, compared to the datum, it go to the downward direction. So the direction will be minus. For the distance it will be 3 foot plus 4 inch. 4 inch is 0.33 foot. So it will be 3.33 and sine 60 degree. Why we can use 9.81? Answer to team. In this problem, we are going to solve the problem in the different unit. We are going to solve the problem in the unit of pound and foot instead of the SI unit. So yeah, we need to try to make the energy to be in the unit of the pound foot square instead of something like in Joule. So for the gravity, we change the unit to be correspond to other variable that we have in the system. So here is G in the unit of the foot per sec square. And I'm not sure when we use the calculator, someone can help me compute the numerical value of the gravitational energy at point 2. Can anyone use the calculator and help me compute this? It's not too big, right? Let me see.
3.33 มาจากไหนหรอครับ
3.33 มาจาก3 ฟุตบวกกับ4 นิ้ว 3.33 feet is come from 3 feet plus 4 inch, which is the distance in the inclined plane, and we need to take the sine theta in order that we have the distance in the vertical direction. And yeah, it should make sense, right? Okay, thank you for the calculation, but I also need to cross check. I'm also not familiar with this unit, but yeah, the number is correct. Thank you, Pooh and team. No, thank you, Pooh. 4639, and the unit should be like per foot square. Is that correct? Yeah, it should correct. Maybe not. Pound and foot per sec square, and pound foot square per sec square. Okay, the problem is here. I forgot to have perfect square for the velocity. So the unit of the energy should be pound-foot square per sec square. Okay, and we have this number. For the kinetic energy and the, oh, I forgot the minus, which means that at point 2, the potential energy due to the gravity at the point 2, the energy is reduced from the initial position because it changed the height downward. For the kinetic energy and the gravitational potential energy, is straightforwardly and it's not difficult for us. For the spring, we may know that the potential energy of the spring, we may familiar with 1/2 kx square for a constant k. But for this case, the spring, the force of the spring, the stiffness of the spring is not constant. We need to try to check, hey, the external force to move the spring, to make the spring deform. From point 1. Point 1 is before the spring deform. The external force that need to make the spring deform from point 1 to point 2. The work is equal to the force multiplied by the displacement in the direction of the displacement. And we know that the spring force is described by the second order function. We have the linear term and the second order nonlinear terms. So for the first position, x1, and the second position is x2 of the deformation. So the integration is the integration of 100x plus 9x squared dx, which is the c. And the limit of integration from point 1 to point 2. At point 1, we set the x at point 1 when the spring has no deformation. The spring has no deformation. For the x at point 2, the spring deformed by 4 inch. The spring deformed by 4 inch. Why we use the unit of x in inch instead of the foot? Because the information that we receive, that we have in the problem, we have the relationship between the force and the displacement measured in inch. The limit of the integration is also written in inch. And for the integral, for the first term, we have 100 x squared per 2 from 0 to 4 inch. And for the second term, we have 9 x power 3 per 3 from 0 to 4 inch. And what is the numerical value of this? Calculator, please. Okay, we have the same value. Thank you, Pooh and Polawat. Okay, the numerical value for this is 992. The unit is the unit of the energy. You may proof check if it's correct or not by the unit. And no. Now the energy here is not in this unit, but it's still in the unit of inches. Why it's super complicated? We need to convert this unit. This unit seems to be the unit of pound inch. Pound inch. We still need to convert this to pound foot. But how to? We know the relationship between pound inch and we know the relationship between the inch and foot, right? So it should be something like 992 per 12 inch per 1 foot. And you can have the unit for the foot. And this gonna be the kinetic, the potential energy in the spring. The potential energy in the spring. In this problem, we still have one more important thing. We have the energy leak by the friction. We have energy leak by the friction. When we consider the friction, we need to draw the free body diagram of the mass, and we need to compute the mechanical work that leak with the friction. So when we draw the free body diagram of the box, we have the box on the slope, and we have mg of the box. We have the normal force, perpendicular to the boundary of the box and the slope. And of course, in the downward motion, we have the friction. We have the friction. If we consider the axis, we may have the x-axis, and we may consider to have the y-axis. We have x and y axis. And mg can be separated into two components. Mg can be separated into two components. And we know the angle 60 degrees. We know the angle 60 degrees. So the summation of force in y direction equal to MAY. Y direction is perpendicular to the slope, and summation Fy is normal force subtract by mg cosine 60 degree. We don't have the acceleration in y direction, so the normal force is equal to mg cosine 60 degree. For the x direction, if we want to find the summation of force in x direction equal to max, we will have some kind of complication. We have mg sine 60 degree and subtract by the friction, it should equal to max. But luckily, we don't need to solve for this complication. We don't need to solve for the acceleration. What we want to know is we just want to know the magnitude of the friction. And in this case, the magnitude of friction also constant. We know that friction is equal to the friction coefficient multiplied by the normal force. So from this, we know that the friction equal to mu mg cosine 60 degree. What we need to do with the friction? We need to know the work done by the friction. We need to know the work done by the friction. The work done by the friction here is the integral of friction force and the displacement from the state 1. The state 0. The state 0. Here is the state 1. And the final motion, not the final motion, the state 2 is the state that we need to consider how much the energy leaked by the friction. So when we need to consider, we need to integrate the f dx from x0 to x2. We know that the friction is constant mu mg cosine 60 degree. We know it's constant, and the integral of the x2 minus x0. So x0, yeah, is 0. And for x2, it's 3. It's 3 feet and 4 inch. It's 3 feet and 4 inch. And this is the magnitude of the friction, the work done by the friction. Can you still hear me? Okay, the work done by the friction. I forgot one thing. The positive x direction is downward, but the friction is opposite to the direction of the x. So by here, we need to have the negative side here. And what we have by u, or the energy leak by the friction, the work done by the friction, is minus 0.5, and the mass 50 pounds. G in this unit is 32.17, and cosine 60 degree, and 3 feet 4 inch is 3.33, and yes, we're gonna compute the work done by the friction, the numerical value, work from friction. And of course, friction always negative, because if the friction has the different in direction from the displacement, the work from the friction always negative. I have one mistake here. I think I have one mistake here. The external non-conservative force, the work done by the external non-conservative force, the total is plus work done by the external applied force and work done by the friction. But as I just mentioned in the example, that U, the work done by friction, always negative. But in this equation, it write in this way. So we have from the work energy theorem, we have external force from the initial position to the final position, and we have the friction work, and we have the delta T, the kinetic energy. What you write Fx equation for? The Fx equation here, no meaning. We don't need it, because we are solving this problem by the work energy theorem. So we need to obtain the normal force by the summation Fy, and we can compose the friction. That's enough. We don't need the summation Fx in this problem. Back to the work energy theorem. We have work by external force. We have work by the friction. It will equal to the change of the kinetic energy plus the change in the gravitational potential energy and the change in the elastic potential energy. So it seems like in this case, it depends on we're gonna consider the spring. If we consider, actually we should consider the spring. The work that external force applied to the spring need to be the the potential energy of the spring. Here, we derive it in this way to see how the energy is added in the spring component, but this energy will appear in the spring as the potential energy of the spring. So by this equation, it seems like we don't have additional external force. We don't have F in this system. We don't have additional external force. And for the friction, if you compute this, you will have something like the negative of the numerical value here. For the kinetic energy, we have T0 and T2. T0 is unknown in the terms of the velocity, and T0 is a constant that we know the value. So here is the delta of the T2 and T0. For the gravitational potential energy at the second stage is the minus of 4639. The initial state of the gravitational potential energy is 0. The elastic potential energy, after the spring is compressed, is stored. This potential energy is stored. The external force, the external work that we need to apply on the spring to this diffraction from 0 to 4 inch is equal to the energy that stored in the spring, the potential energy that's stored in the spring. And of course, we know we can compute the number, and we know the potential energy that's stored in the spring, the elastic component at the state 2. Before the spring deform, the potential that's stored in the spring before the spring deform at point 1 is 0. So yeah, now you know this, you know all of this. This is 0, and you know the work by the friction. And yeah, we can solve for the numerical value of the speed. Yeah, we may confuse the concept is also not easy to understand, and we also have the confusion due to the unit. But yeah, please take time to recheck the step to solve this kind of problem again. But for today, this example may be the most difficult one, because we have all the effect in the energy terms. We have the friction, we have kinetic, have potential energy relationship, and we also have the slope. The next question may be, the next example may be a little more easy. Let's see. In this example, the initial position of a collar is here, a collar and a rod. We apply a force, constant force with the magnitude of 50 Newton, and the angle of the force is in this direction, 30 degrees with the vertical direction. And the force is constant in magnitude and constant in the orientation until here. Under the effect of the force, we make the collar 2 kilogram collar. We make the collar move upward to the B position. If we have only force and the mass of the collar, the problem is not that complicated. But if we see, we also constrain the collar by a linear spring with a spring constant K. The unstretched length of the spring, L0 of the spring, is equal to 1.5 millimeter, 1.5 meter. It means that in this condition, the spring is already stretched. Also in this condition, when the collar moves to point B, the spring is also under stretch. By the geometry, what we can see, here 1.5, here 2 meter. At this point, the length should be 2.5 meter, is what we can see from the geometry. So again, what the problem give, the problem said the mass 2 kilogram, the mass 2 kilogram. L0 of the spring, 1.5 meter. The stiffness K of the spring, 30 Newton per meter. At point A, release from rest at point A. It means the speed at point A equal to 0. And the information of the force magnitude is 50 Newton and angle 30 degrees for the force. And what we need to find, what do we need to find? We need to find the velocity at position B. We need to find VB. From the last example, what we don't have in the last example is this one. We don't have the work done by the external force, but here, what is the work done by the external force to move a collar from point A to point B? What is the work done by external force to move a collar from point A to point B? It equal to the force in the vertical direction. The force in the vertical direction multiplied by the distance that the collar move, the distance, maybe distance S, maybe, that the collar move. But yeah, we can obtain the numerical value. The magnitude of force is 50 Newton, cosine 30 degrees, and the displacement 1.5 meter. So by use the calculator, we may have something like, in the unit of Joule, for the work done by the external force at point A, what is the other terms of energy at point A? What is the kinetic energy at point A? What is the kinetic energy at point A? Kinetic energy is 1/2 mv square. At point A, no velocity, so kinetic energy is 0. How about the gravity at point A? The potential energy due to the gravity at point A. Again, we're gonna set the datum here. So at point A, the height is 0. How about the spring? The elastic potential energy at point A. 1/2 K x minus L0 square. 1/2 K x minus L0 square. L0 is 1.5 meter, but at point A, the spring is under stretch by to the length of 2 meters. So the potential energy is 1/2. K is 30. And 2 subtract by 1.5 square. Maybe here at point A. How about at point B? At point B, what happened at point B? The kinetic energy is 1/2 mv at point B square, and we still don't know the speed, but we know the mass. We know the mass. And it's still in the unknown of the speed at point B. How about the gravitational potential energy at point B? At point B, the mass 2 kilogram G, and the height at point B, the height of the center of mass will be 1.5 meter. How about the spring? The elastic potential energy at point B. The elastic potential energy at point B, 1/2 K, and XB minus L0 square. The length at point B, the length already be 2.5, right? So maybe just 15 June. Come back to the work and energy relationship, the principle. The governing equation is, hey, the external work applied by the external force, the work done by the external force, plus the energy leaked by friction. Energy leaked by friction, or the work done by friction, will equal to the change in the kinetic energy plus the change in the gravitational potential energy plus the change in the elastic potential energy. We don't have friction in this system. Wow, they didn't mention about the friction, right? Oh, wow, still lucky. Okay, the work is this one. The work is this one. The friction is 0 in this case because it's smooth rod. The friction 0. The TB is what we need to find because we need to find the VB square. TA is 0. The gravity at point A also 0. And we compute the gravity at point B. The elastic, we have the elastic at point A and elastic at point B. But yeah, finally we can solve for the speed. You may try to recheck, but the value should be something like for the VB. And the last example for today. We have the linkage.
Teacher, what number you get? Last question.
This one. The velocity at point B, 4.926 meters per second. Okay, for this example, the last example for today, we have a structure like here, and it only moves on maybe XC plane, in the vertical plane only. And we have the collar here on a smooth rod. A collar on a smooth rod where it's smooth. They didn't talk about the friction again, but yeah, let's neglect the friction. We have the mass here, 4 kilograms. The mass 4 kilograms can move up and down. And when it moves downward, it will compress the spring. The spring has the K constant. And also they have arm of the linkage. At the arm of the linkage, they connect to 3 kilograms for the right hand arm and connect to another 3 kilograms for the left hand arm. And they give the length, the parameter here. They also give one information that it starts from rest and uncompressed spring. It starts from rest and uncompressed spring. When the theta here is equal to 180 degrees, we have theta and we have theta per 2. And of course, we know that this length gonna be 0.2 meter psi theta. Does that make sense? 0.2 meter psi theta. 0.2 meter psi theta per 2. And this length also equal. So the problem at the first stage, when the block doesn't move, the theta is 180 degree. The spring stiffness is 900 Newton per meter. We have mass 4 kilograms and we have mass 3 kilograms. We have 2 of the mass 3 kilograms. And what we need to find is the theta B. Theta B means after we let it move. After we let it move, the collar will move downward due to the effect of the gravity. The gravity try to push the collar downward. The gravity also try to push the arm downward. So this three combination of the effort, it try to move the 3 kilogram sphere downward on both sides of the arm. The gravity also try to move the collar downward. The collar only have the spring force to resist the downward motion. The collar only have the spring force to resist the downward motion. We need to compute, we need to find the angle at the maximum compression, of the spring. For me, I assume that at maximum compression, this theta angle will be theta B. Before it moves, theta at A point is 180 degrees. Theta at the B point will be the theta at max compression. Today, we're gonna solve this problem by using the work and energy theorem. If you consider this only in the static case, you may can find some equilibrium of force, equilibrium of the spring force, and equilibrium of force pushed downward by the 4 kilogram, and the force pushed downward by the mg of two sphere, and transform it to the force inside the ring. You may have an answer in the static case, the static equilibrium. But my question is, do you think the maximum compression will be the same position as the static equilibrium of this system or not? Yes, Polawat, I hope you may get the concept. We have the maximum compression. We have the maximum compression and static equilibrium. If we simplify the system to be 1 degree of freedom spring and have a mass of course, for the static equilibrium, the spring may deform with some length. The spring may deform with some length so that K delta X 0 is equal to mg. The static equilibrium, the spring constant multiplied by the static displacement equal to mg. We can obtain the displacement at static equilibrium. At static equilibrium, acceleration at the static equilibrium, summation of force in the vertical direction equal to 0. At static equilibrium, summation of force in the vertical direction equal to 0. It means the acceleration in the vertical direction equal to 0. Here is the explanation of static equilibrium. But for the maximum compression, what should be the condition for the maximum compression? Delta X max. What should be the condition for the maximum compression? The delta X will be the delta X max if it switches the direction of motion from downward motion to upward motion. The maximum compression will be the position that the velocity switch the direction from downward velocity to the upward velocity. So what should be the speed at the switching point? What should be the speed at the switching point? When the velocity change the direction, it needs to change from positive velocity to the negative velocity. At that point, the speed will be 0. From the positive switch to the negative. At that point, the speed will be 0. So this problem, we need to find the maximum compression. So it means the speed at that point equal to 0. The speed at that point equal to 0. So we need to find the theta at max diffraction. In this case, it means at that point, the 4 kilogram mass don't have speed. The 3 kilogram mass also have 0 speed at that point also. So how can we find the theta B? How can we find the theta B? At the initial condition at point A, the kinetic energy also 0 because at point A, it released from rest. So nothing move when it begins. Nothing move. The mass 4 kilogram don't have speed. The mass 3 kilogram don't have speed. The kinetic energy is 0 at point A. How about the gravity? The potential energy at point A. If we set here as datum point, okay, maybe it's not that good. I mean, we're gonna set the let's set maybe this pin position maybe let's set this pin position as a datum point. The height of mass 4 kg, the height the 4 kg is mass 1, the g and the height of the mass 4 kg, and we have 2 of mass 3 kilogram with the height of the mass 3 kilogram. The height, the mass of 4 kilogram G, the height of mass 4 kilogram, the height of mass 4 kilogram will equal to 0.2 meter sine of theta 0.2 will be this, and plus this, we will have the height of the mass 4 kilogram. So H1 is equal to 0.2 sine theta per 2 multiplied by 2, because this arm and this arm has same length, and the angle here theta per 2 are the same, so the vertical height are the same, and the H1 need to be the 2 multiplied by this length. For the second term, the height of mass 3 kilogram, 2 m is equal to 3 kilogram G, and the height H2, we need to find the angle. The height will be this still be theta per 2. This angle still be theta per 2. Does that make sense? No. It should make sense, right? Yeah, this angle is equal. So the height of the mass 2 is equal to 0.5 and sine of theta per 2. 0.5 is this length, sine of theta per 2 will be this. But at point A, we know the theta at point A. The theta at point A is equal to 90 degrees. So yeah, you can compute the numerical value of the potential energy at this point. The elastic potential energy at point A, it starts from raised and uncompressed spring. It means uncompressed spring. The kinetic energy in the spring also 0 at point A. What happened at point B? At point B, or at the maximum compression, at maximum compression, The speed also 0 if the inverse motion, the position of the inverse motion from downward to upward motion. At point B, the kinetic energy also 0. TB at point B also 0. The gravitational energy at point B. At point B, we don't know the zeta. We don't know the zeta. But the formation of the zeta at point B and at point A, the formation are the same. Just we have the difference in the zeta. So how can we form? We can write down from here. It's gonna be M1 and G. M1 and G, and H will be, H1 will be H1 will be 2 multiplied by 0.2, which is 0.4, and psi of zeta B per 2. And for the mass 3 kilogram, we have 2 sides of mass 3 kilogram. The energy will be 2 of the mass 3 kilogram multiplied by G and multiplied by the height of the mass 3 kilogram. The height will be 0.5 multiplied by psi zeta B per 2. We know the mass 1, 4 kg, the mass 2, 3 kg, and we know the value of G. Yeah, finally, we can write this by 4 multiplied by 0.4, 1.6, 1.6 plus 6 multiplied by 0.5 plus 3, and G and psi theta B per 2. Here is gravitational potential energy at point B. It will be written in the term of constant and the unknown zeta B, How about the elastic potential energy at point B? It's already complicated for the elastic potential energy at point B. Let's begin the next page. At maximum diffraction, YVB is 0. Okay, YVB is 0. B is the position with the maximum compression. the position with maximum compression. The idea is when we have a spring and we drop something here, the velocity will be in the downward motion and the spring will compress to one direction, and before it reverses the speed to the upward motion, at the point that it switches the direction of the speed from downward speed to the upward speed, at that moment velocity will be 0, and at that moment it corresponds to the maximum deformation, maximum compression point when the velocity change the direction. In our system also, the mass going downward, but at one point that the spring has the maximum deformation, the velocity will change the direction from downward to upward. And at that point, the velocity will be 0. Okay, we still need to find the elastic potential energy at point B. At point B, the elastic potential energy is equal to the deformation in the spring. Okay, the deformation, the elastic potential energy is 1/2 multiplied by K and multiplied by the deformation of the spring. Deformation of the spring. So at point B, what should be the deformation of the spring? What should be the deformation of the spring? At the uncompressed position, the height of the height here at the compressed position, the block moved to somewhere and the height of the spring decreased. So the difference between the length of the spring is equal to the difference between the position of the mass. The difference between the length of the spring is equal to the difference between the position of the mass 4 kg. In the original state, the position of the mass 4 kg is 2 multiplied by 0.2 psi theta/2. Here, the distance here is 0.2 psi theta/2. When we multiply by 2, we can get this distance. So in the beginning, the mass 4 kg had this height, and at theta A, when it transforms, it compresses the spring. When it compresses the spring, okay, and before it compresses, theta A is equal to 180 degrees. After it compresses 0.2 psi theta B, that we still don't know the theta B. And we know K, right? We know K. 900. So we can form the elastic potential energy in the terms of unknown. It can be 1/2 of 900. And here, theta A is 180 degrees. 180 degrees per 2 is 90. So we have 0.4. The second term, we also have 0.4 multiplied by psi of unknown angle. Or it can be 450 multiplied by 0.4 and multiplied by 1 subtract by psi theta B per 2. And now we construct or the term for the work energy principle. From the work energy principle, the work from external force, the work leaked by the friction, the energy leaked by friction will equal to delta of the kinetic energy, delta of the gravitational potential energy, and delta of the elastic potential energy. We don't have external force. We don't have friction. And the TB and TA is start from rest, TA 0. At the maximum compression, TB also 0. The gravitational potential energy, we can compute the numerical value of VGA. And for the VGB, it's still in the terms of unknown of the constant multiplied by psi theta B per 2. VGA is constant. VGA is a constant. VGB is something multiplied by psi theta B per 2. The elastic potential energy for A, VEA, elastic potential energy is 0. The string is not compressed. For the B, VGB, is also something constant and something multiplied by the psi theta B per 2. So by solving this equation, of course, we can solve for the theta B. So yeah, that's all for today. Sorry for the delay. We have about 10 minutes late. Sorry. Do you have any questions? โอเคขอบคุณครับ
อาจารย์ครับผมมีคำถามข้อสไลเดอร์ครับ
ครับเดี๋ยวเปิดให้แป๊บหนึ่งตอนนี้ผมยังแชร์อยู่แป๊บนึงนะคนที่ไม่มีคำถามคลาสจบแล้วนะครับ แต่ว่าที่มีคำถามเดี๋ยวแชร์ให้ ข้อสไลเดอร์
ครับ
แป๊บนึงสไลด์โอเคครับ ถามว่า
example 1ใช่หน้าที่แล้วครับผมตรง u ขีด1 ถึง 2อะครับ
ครับ
ผมไม่เข้าใจว่าทำไมหน่วยมันถึงไม่เหมือนตัวอื่นทั้งที่มันน่าจะเหมือนกันหรือเปล่าครับ
แป๊บนึงอ๋อ
มันเป็นป
ต
อ
ร
น
ง
ด์
นี้
คูณ
ตรง
ฟิต
นี้แป๊บนึงแป๊บนึงนะทำไมมันถึงออกมาเป็นปอนด์อินช์นะแป๊บนึงปอนด์ทำไมถึงได้ปอนด์อินช์วะ
คือมันควรจะเหมือนตัวอื่นใช่ไหมอาจารย์
เดี๋ยวดิแป๊บนึงทำไมตอนนี้ผมถึงเขียนปอนด์อินช์มาวะ F คูณ S W เดี๋ยวนะเท่ากับ F S ผมน่าจะสับสนอะไรบางอย่าง แต่ว่าแป๊บนึง
เพราะว่าตรงตัว C ในกราฟมันเขียนว่า LV หรือเปล่าครับ
มันคือปอนด์ทำไมผมได้ปอนด์อินช์ออกมาวะแป๊บนึงจริงๆโอเค ตรงนี้มันควรจะเป็นปอนด์ถูกปะ
ครับ
ตรงนี้มันควรจะเป็นปอนด์แล้วมันก็อินทิเกรตกับอินช์ออกมา มันเลยเป็นปอนด์อินช์เนี่ยนะ เดี๋ยวแป๊บนึงทำไมวะปอนด์อินช์แปลงเป็นปอนด์ฟุตแต่ว่าถ้าหน่วยของ energy จริงๆมันต้องเป็นปอนด์ฟุตสแควร์เปอร์เซกสแควร์ทำไมวะแป๊บนึงจริงๆ work มันควรจะมีหน่วยเป็นปอนด์ฟุต work มันควรจะมีหน่วยเป็นปอนด์ฟุตมันไม่น่าจะมีอะไรขัดแย้ง แต่ถามว่าทำไมตัวพวกนี้มันถึงสมมุติถ้าเป็น mv สแควร์1/2 mv กำลัง2หน่วยมันควรจะเป็นอะไรวะมันก็เป็นปอนด์แล้วก็ v สแควร์ทำไมหน่วยมันไม่เหมือนกันวะว่ะผมไม่เคยดูตรงนี้เลยว่ะต่อให้เป็นหน่วย SI ที่เราคุ้นเคยจริงๆต่อให้เป็นหน่วย SI ที่เราคุ้นเคยจริงๆมันก็จะเป็นกิโลกรัมแล้วก็เมตรสแควร์เปอร์เซกสแควร์ถูกปะ
ครับ
แล้วหน่วยของ work ที่เราคุ้นเคย มันก็คือเป็น force คูณกับระยะทาง force มันคือ ma ระยะทางมันคือ s ถูกปะ m มันคือกิโลกรัม a มันคือเมตร per sec square แล้วก็ระยะทางมันก็คือเมตร เพราะฉะนั้นถ้าเป็นในหน่วย SI เรายังจะได้กิโลกรัมเมตรสแควร์ per sec square เท่ากันอยู่ แต่ว่าทำไมตัวนี้มันถึงสักครู่
ไม่เท่าครับอาจารย์ในตัว v มันคือกิโลกรัมคูณเมตรกำลังสองส่วนเซกกำลังสี่ครับเอ้ยถูกแล้วโทษทีถูกแล้ว
เดี๋ยวถ้าเกิดเป็นหน่วย SI work มันคือ ma คูณกับระยะทาง หน่วยของ force มันคือกิโลกรัม ผมว่าผมเข้าใจแล้ว โอเค เรายังอยู่ป่ะคนที่ถามผม
อยู่ครับ
โอเค หน่วยปอนด์ฟุตเนี่ย มันมีปอนด์ฟอสกับปอนด์ที่เป็นปอนด์แมสอะ
อ๋อในที่นี้คือปอนฟอสใช่ไหมฮะ
ใช่ในที่นี้คือปอนด์ฟอส
อ๋อ
ถ้า
ที่
จะ
มัน
แต
โช
ก
ว์
อ
ใน
อก
ก
มา
รา
เป็
ฟ
นปอนด์แมสมันก็คือมันเป็นปอนด์คูณอยู่กับความเร่งอะ
อ๋อ เข้าใจแล้วครับ
เออ
คือมันมีตัวพิเศษอย่างนี้ด้วยใช่ไหม
ขอบใจมากว่ะผมก็โง่เหมือนกันว่ะแต่คุณเข้าใจใช่ไหมว่ามันมีปอนด์ฟอสกับปอนด์แมสปอนด์ฟอสมันคือเอาปอนด์ไปคูณกับความเร่งอ่ะความเร่งมันก็คือฟุต per sec square อ่ะจริงๆไอ้ตัวเนี้ยมันคือปอนด์ตัวนี้มันคือฟุตปอนด์คูณกับฟุต per sec square
อ๋อแต่เขาเขียนย่อๆใช่ไหมครับ
ใช่ในเนี้ยไอ้ปอนด์ตัวเนี้ยจริงๆมันคือปอนด์ฟุต per sec square
อ๋อ
โอเค
โอเคครับ ขอบคุณครั
ชั
บ
ดเจนขอบคุณมากคุณก็สอนผมด้วยโอเคไม่น่ามีคำถามแล้วเนาะมีอะไรก็ทักมาถามแล้วกันครับวันนี้ขอบคุณมาก